So here we have a box on a ramp, and we want to first start by saying it wouldn't hurt to say that the sum of our forces is going to equal mass times acceleration. Now the sum of our forces means that it has to be specifically in the x or specifically in the y direction. But however many forces we have, we should be able to add them all up together, and it will equal the mass of the object times the acceleration of the object. So the next step would be to create a force body diagram. In this situation we have the force of weight, which is straight down. It is also equal to 65 newtons, since 6.5 times 10, we'll use 10 as the acceleration due to gravity. 6.5 times 10 is 65. Okay, because this angle right here is 35 degrees, the angle between the perpendicular and the force of weight here is 35 degrees. Alright, now what we're trying to find, what we want to know, is what is the normal force being applied perpendicularly to the surface of the ramp, and also what is the force down the ramp. Okay, these are both going to be proportional to the force of weight depending on at what angle they are. Okay, now if we solve for the opposite of this 35 degrees, we're solving for this side. Notice that this force vector is equal in magnitude and direction to this force vector. So if we can solve for this, we can solve for the force down the ramp. Notice that our hypotenuse for this triangle is our 65 Newton force of weight. So the force of weight, or the force of weight in this direction down the ramp, that component will be the force of weight, which is 65, sine theta, so sine 35. Our normal force in the y direction is going to be 65 cosine 35. Okay, so we're going to make sure that our calculators are in degree mode. Okay, mine currently is. And I'm going to type in 65 sine 35 to get me my x. So that's 37.3 newtons. And I will plug in 65 cosine 35 to get my normal force, which is 53.2 newtons. Alright, the reason that the sine and cosine are flipped for this is because normally our y is our opposite. Okay, notice that when we're using this angle, our fx, it now becomes our opposite, and this side, which will be our equal and opposite to our normal force, will be our adjacent. Alright, so it says if the angle decreases the force down the ramp, so if we make this ramp go down, so the angle is decreasing, then this is going to get smaller and smaller and smaller, while the normal force gets bigger and bigger and bigger. So if the angle decreases, the force down the ramp decreases. Okay, for instance, let's make this angle decrease. Let's say that it's 10 degrees instead of 35. I'm going to plug in 65 sine 10. Okay, notice that where before we had 37.3, now we only have 11.3. Okay. Now, if the angle increases, the normal force is also going to decrease. So if the angle increases, normal force decreases. Okay? Until the ramp becomes all the way vertical, in which case you would have absolutely no normal force. So let's say that our angle increases. So let's take it from 35 to 50. Okay? So calculate 65 cosine 50 for our normal force. Notice that our normal force is now smaller, 41.8, compared to before. So as the angle increases, the normal force gets smaller and smaller and smaller. Alright, it says calculate the object's acceleration. Well, we know that we have a force down the ramp that is parallel to the ramp, so we'll call that the x direction. It's 37.3. But we also know that we're going to have an opposing frictional force. Well, if it wants us to calculate the object's acceleration, that implies that the object is going to be moving. So, since it's moving, we're going to use kinetic, right? The slipping frictional force. Notice that we can't use static friction because static implies that it's at rest. And if it's accelerating, it is definitely not at rest. So our frictional force, so Fk, is going to be equal to mu times the normal force, where mu was 0.12 and the normal force we calculated is 53.2. So we'll multiply those two together. 0.12 times 53.2, and we get 6.4. So we have 6.4 newtons of frictional force opposing this on the other end. Now, since this is to the left, it's technically negative. So when we go to plug in the sum of our forces, we get 37.3 minus the 6.4, and that all equals mass times acceleration. Well, the mass is 6.5, and we're solving for acceleration. So 37.3 minus 6.4 is 30.9, and then 30.9 divided by 6.5 will give us our acceleration, which is 4.75. So A equals 4.75 meters per second squared. Okay. If the object is 3.5 meters up the ramp and it starts at rest, okay, it's a clue there, how fast is it going to be going at the bottom of the ramp? Alright, so we know a few things. We're going to have to use the kinematic equation. We know since it started at rest, our initial velocity is 0 meters per second. We also know that the object went 3.5 meters. So our displacement is 3.5 meters. And we know our acceleration because we just calculated it up here, 4.75 meters per second squared. We don't have or want time, and we want to calculate how fast it's going at the end, the final velocity. So we are going to use the equation without time, which is final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. So our final velocity is what we're trying to solve for. Initial velocity was 0. Well, 0 squared, still 0. And then 2 times the acceleration, 4.75, times the displacement, which is 3.5. So we're going to multiply all these numbers out and take the square root of them. And that should give us our final velocity. So 2 times 4.75 times 3.5, and we get 33.25. I'm going to store that answer as x and take the square root of x. 5.77 meters per second, since we're talking about the final velocity. And that is our answer.